Hey everyone, glad you could join us today. We are diving into one of the most mind-bending concepts humans have ever tried to understand, the speed of light. If you enjoy exploring the mysteries of the universe with me, then feel free to like the video and subscribe, and tell me where you are watching from in the comments. It is always amazing to see people from all over the world looking up at the same stars. Now let us relax and enjoy this journey together as we explore what it really means to move at the speed of light. Moving at the speed of light is not just about going fast. It is about reaching the ultimate limit that the universe has set for motion. Light travels at about 300,000 kilometers every single second. That means in the time it takes you to blink, a beam of light could go around Earth almost 8 times. It is not just fast. It is the fastest anything can move through space as far as we know. Nothing with mass can catch up to light. Nothing can outrun it. Light speed is the cosmic speed limit. But what does that actually feel like? Imagine you are on a spaceship built to go faster and faster. As your speed approaches the speed of light, something strange begins to happen. The universe you know starts to warp around you. Time slows down for you compared to everyone else. Your clock ticks slower, your heartbeat slows. If you spent a few years traveling close to light speed then returned to Earth, you might find that decades or even centuries have passed here. Your family, your friends, entire civilizations might have changed while you barely aged at all. This effect is not science fiction. It is a real consequence of how time works when you move fast. Space also begins to change. The direction you are traveling in seems to stretch. The starlight ahead of you grows brighter and shifts toward blue and ultraviolet. Meanwhile, the universe behind you stretches into darkness. It is like being pulled into a cosmic tunnel where everything in front of you is being squeezed and everything behind you is fading away. Distance and direction become slippery ideas because space itself bends around motion. To move at the speed of light is to move at a pace the human mind can barely grasp. The numbers stretch our imagination. 300,000 kilometers every second, almost 1 billion kilometers every hour. In just 1 year, light travels nearly 10 trillion kilometers. That distance is so large we had to invent a special name for it. A light year. When astronomers measure the size of the universe, they are not counting miles or kilometers. They are counting time itself. When you look at a star 40 light years away, you are not seeing it as it is today. You are seeing it as it was 40 years ago. Light is fast, but space is huge. So everything we see in the universe is really a view into the past. The closer you get to the speed of light, the more your everyday reality starts to fall apart. Things you always believed were fixed begin to wobble. Length, mass, time. They all depend on how fast you are moving. If you were racing near light speed across the galaxy, your bones and your muscles would feel heavier because motion adds energy, and energy behaves like mass. Even the shape of your spaceship would change. To someone watching you from far away, your ship would look squished shorter in the direction it is moving. This is not an illusion. It is the universe adjusting itself to protect the speed limit. And if you finally reach the exact speed of light, something astonishing would happen. Space and time themselves would refuse to behave normally. No more seconds ticking by. No more distance stretching out ahead. For light, there is no journey, no wait, no aging. A photon born inside the core of a star travels across galaxies for billions of years from our point of view. Yet from the photon's point of view, the beginning and the end are the same moment. It is like existing inside a doorway that never opens and never closes. Imagine experiencing the entire lifetime of the universe in a single instant. That is what the speed of light does to time. The universe guards this rule carefully. The faster you go, the harder it becomes to keep pushing. Going from half the speed of light to 3/4 takes a lot of energy. But going from 99% to 99.99% takes far more. Every extra piece of speed costs more than the piece before. as if the universe is saying, "Slow down, you have come far enough." There is a final barrier ahead, and only light is allowed through. But humans are dreamers. We look at the stars and imagine ourselves gliding across them like cosmic explorers. We build machines that fly faster than anything before. We accelerate particles in giant underground rings to speeds closer and closer to light. We learn from every attempt. We discover new physics hidden in those limits. Even though we cannot reach the speed of light, we keep chasing it because chasing it is how we learn what the universe is made of. And the universe is clever. It has another path waiting for us, a loophole. Instead of going through space, we could bend space. If you curl a map and bring two faraway points together, the journey becomes short. Scientists call this a warp or a wormhole. Not speeding up, not breaking the rule, just changing the shape of the road. It is still theory, still distant, still wrapped in the unknown. But ideas like that show us how curious and determined humans can be. If one day our technology catches up to our imagination, we might fly between stars in the blink of an eye. We might watch whole galaxies pass like scenery outside a window. We might discover new worlds and new kinds of life. We might learn what lies beyond everything we have ever seen. And when that future comes, we will look back at this moment and smile because this is where the dream began. For now, we live in a universe ruled by light. It defines what is possible and what is impossible. It shapes our understanding of time. It connects us to the past and guides us toward the future. We are creatures built from matter that cannot reach light's speed, but our thoughts can. Our curiosity travels faster than any rocket. Our questions leap farther than any probe. And as long as we keep imagining what it would be like to ride a beam of light across the stars, we will continue to grow, continue to learn, and continue to push the limits of what humanity can become. If you tried to add more and more energy to your ship as you get closer to light speed, something surprising happens. You do not accelerate much faster. Instead, your mass begins to increase. You become heavier in a way. The universe resists you. And the closer you get to that final barrier, the more energy you need. To actually reach the speed of light, you would need infinite energy. And no matter how powerful a rocket or engine you build, infinity is not something you can ever supply. That is why light speed remains unreachable for anything made of matter. Light itself does not face this problem because photons, the particles of light, have no mass at all. They do not feel time the way we do. For a photon leaving a distant star, there is no sensation of travel. It leaves and arrives in the same instant from its own perspective. For light, the entire universe exists in a kind of eternal now. That alone changes how we think about reality. For everything else, time flows. For light, time does not even exist. Moving at the speed of light would change your very experience of being alive. You would be frozen in a moment that never ages, while the entire cosmos rushes into the future without you. The world you left behind would fade into history. Generations would pass. New stars would be born. Old stars would die. And to you, none of it would feel longer than a heartbeat. Light-speed travel is not just fast travel. It is stepping outside the normal rhythm of time itself. So, when we dream of ships that glide across galaxies in a single burst of speed, we are dreaming about breaking the universe's most sacred rule. We are dreaming of touching something that nature keeps just out of reach. Yet that dream keeps us curious. It pushes us to explore physics deeper, to question what is possible and what might someday be possible. Because somewhere far into the future, maybe humans will learn how to bend space instead of racing through it. Maybe we will fold distances so that stars which seem impossibly far can be reached in moments. For now, though, we stand on the edge of knowledge and stare toward the horizon, where light travels freely and time stands still, and we wonder what it would feel like to catch it. Moving at the speed of light means changing reality as we know it. It means letting go of ordinary rules and stepping into a place where space and time twist together. It means exploring the deepest mysteries written into the universe itself. And the beautiful part is that even if we can never ride alongside a beam of light, the act of imagining it already takes our minds farther than our bodies can ever go. Could anything ever move faster than light? It is such a tempting question because when we look at the universe, so huge and full of distance, our minds almost scream that there has to be a shortcut somewhere. Light feels like a rule that is daring us to break it. But the strange thing is that the universe is not just enforcing this speed limit because it wants to be annoying. There is something deep and powerful about the structure of reality that locks this rule into place. When something with mass speeds up, its energy changes its very identity. It becomes more difficult to push forward, almost as if it is carrying more and more of the universe on its back. You can pour energy into it all you want, and instead of making it faster, the universe keeps transforming that energy into more mass, like adding bricks to a backpack while trying to sprint. When something reaches 90% the speed of light, pushing it further feels like trying to push a mountain. At 99.9%, the entire universe would have to shove it, and it still would not reach the finish line. Infinite energy is no joke. It is simply something the universe does not allow us to have. Light avoids the problem by being weightless. It does not have to wrestle with mass or slam particles aside to rip through space. It just glides effortlessly, as if space itself is built to let it pass. It is the universe moving information from one place to another in the most perfect way possible. It is the speed of reality updating itself. That is why it is so special. It is not just fast. It is the speed that defines what speed even means. Yet even with that unbelievable power, light has limitations. There are places it has never reached, places that may always remain dark, far away. The universe is stretching faster than light can move, carrying entire galaxies off beyond our reach. They are not accelerating through space faster than light, but space is carrying them like leaves drifting on a river current that speeds up without warning. If you look far enough into the distance, you are looking at objects already lost to us forever. The light they send right now will never catch us. They are drifting into a part of the universe where distance grows faster than a beam of light can chase. That alone is proof that light is not the ruler of absolutely everything. It just rules the part of space that stays still long enough to be crossed. And this makes scientists wonder, what if there are ways to cheat the system, not by breaking the rules, but by bending them? Our universe is not a rigid box. It curves and warps around heavy objects. Black holes bend space so strongly that inside them, falling inward is like sliding into a well so deep that the bottom is not even a place anymore. If space can twist and fold, then maybe one day we could convince it to fold for us. A warp bubble could shrink the distance in front of a ship while stretching the distance behind it. You would not be moving faster than light. The space around you would just decide to take a shortcut. No speed record broken, no cosmic police knocking at the door. Or maybe the universe has secret tunnels, wormholes that connect distant areas of space the way hidden hallways connect two rooms without using the main corridor. If a wormhole could be held open, a spacecraft could travel between stars without crossing the space between them. It would feel like breaking the light speed limit, but really, you just change the rules of the path. Then there are tachyons, the mysterious idea of particles that could only exist faster than light. They belong to a world where slowdown, not speeding up, requires infinite energy. If they exist, they would completely break our understanding of cause and effect. A message could arrive before it was sent. A moment could be undone by the very event that caused it. Time itself would lose its order like pages of a book scattered in the wind. For that reason alone, the universe seems to hide these creatures if they are real at all. Maybe the cosmos does not want to live in a place where the future and past can argue about who is more real. Every rule feels unbreakable until someone finds a larger rule behind it. Human history is full of ideas that seemed impossible until someone decided to believe they were not. We once thought the sound barrier was unbreakable. We once thought the ocean was the edge of the world. We once thought flying belonged only to birds. Every generation has its own version of impossible. Light speed might be ours, but impossibility is funny. It only stays strong until a curious mind arrives. It could be that the universe is a much more playful place than we understand. Maybe it has left clues lying around that hint at realities faster than light. Maybe dark energy is nudging us to look closer. Maybe the fabric of space-time is less like a flat road and more like a living thing that can twist and shift if we learn how to speak its language. Imagine someday that traveling across the galaxy feels like stepping across a puddle. Imagine explorers moving not by speeding forward, but by making the universe move around them. Imagine distances collapsing, like they were never real in the first place. Light would not feel like the finish line anymore. It would feel like the starting point, a relic of how travel worked before we learned that speed is not everything. So can anything move faster than light? Today our universe seems to say no in the loudest voice possible. But buried underneath that no is a quiet whisper that says maybe you are just asking the wrong question. Maybe the secret is not to go faster than light, but to discover that there are other ways to travel, other ways to explore, other ways to exist in a universe that is more mysterious than our speed limits suggest. And if one day we do find a way to beat light, not by breaking rules but by outsmarting them, then future generations will look back at us with the same amazement that we look back at candlelight and wooden ships. They will wonder how we ever thought the universe was small enough for speed to matter. They will step out into the stars and realize that the impossible was never a prison. It was a challenge, and we were always meant to rise to it. Light is often described as the fastest thing in the universe, racing across space at an incredible 300,000 kilometers per second. Yet even light faces challenges on its journey. In a perfect vacuum, light can travel forever without slowing down, without losing energy, seemingly unlimited in distance. But the universe is not perfectly empty. Even in the vast voids between galaxies, there is a subtle presence of particles, stray photons, magnetic fields, and cosmic dust that can interact with light in minute ways. Over enormous stretches of time, light can be absorbed, scattered, or redshifted as the universe itself expands, stretching the wavelength and decreasing the energy of photons, making them cooler and less energetic. When we observe the light from distant galaxies, we are not seeing them as they are today, but as they were billions of years ago. The farther the light has traveled, the more the universe has expanded during its journey, and the more stretched its wavelength has become. Ultraviolet light from the earliest stars, for instance, has been redshifted into the infrared, and some of the light that began its journey shortly after the Big Bang now exists as the cosmic microwave background, a faint whisper of the universe's infancy. The expansion of space itself imposes a kind of practical limit on how we can perceive light, though not a true limit to its travel. In theory, a photon could continue indefinitely, moving across an empty cosmos. But in practice, the universe constantly changes, and its expansion stretches light across scales we can barely imagine. Light can also be trapped or redirected by massive objects. Black holes, for example, bend the fabric of space-time so sharply that light cannot escape if it crosses the event horizon. Around these cosmic giants, light can orbit, spiral, or be captured forever, never reaching a distant observer. Gravity from galaxies and clusters can lens light, bending it into arcs, multiplying images, and changing paths. This means that while light may travel immense distances, it is never traveling in a straight line unchallenged. Its journey is shaped by the mass and motion of everything it passes, a silent story of the cosmic terrain it traverses. Even more subtle is the effect of cosmic dust and gas. While most of space is empty, the light that travels through galaxies encounters clouds of matter. Some photons are absorbed, re-emitted at different wavelengths, or scattered in unpredictable ways. This does not stop light in the same sense that a wall would stop a particle, but it does mean that after billions of years, a significant portion of the light emitted by early stars has been diffused, transformed, or converted into other forms of energy. The universe, while largely transparent, is not perfectly clear. Over long distances, the cumulative effects of interactions can alter light, creating a practical horizon beyond which the original photon is no longer recognizable. Another limiting factor comes from the expansion of the universe itself. Space stretches continuously, and as it does, it increases the distance between objects faster than light can traverse them. There may be galaxies and regions so far away that their light will never reach us, no matter how long the universe exists. These regions are moving away from us faster than light due to the expansion of space, not because the light itself is slowing, and this creates a cosmic limit to what we can see, sometimes called the observable universe. Even if light could continue indefinitely, it may never reach certain points because space itself is growing beneath it, widening the gap beyond any possibility of traversal. Yet, despite all these factors, light remains a remarkable messenger. It carries information from the farthest reaches of the cosmos, letting us study stars and galaxies billions of light years away, reconstructing the history of the universe. Every photon that reaches our telescopes has survived an incredible journey, moving through expanding space, past massive objects, through interstellar and intergalactic matter, and across epochs of time. The fact that it arrives at all is astonishing, and it reminds us that even though practical limits exist, the potential for light to continue is infinite in principle. There is also a philosophical dimension to this question. If light travels forever, does it truly have a limit? Or is the limit only in our ability to perceive it? Our eyes, our instruments, and our understanding impose boundaries. Yet beyond these human limits, light may be streaming through vast emptiness, endlessly, without stopping. Each photon can, in theory, keep moving for trillions of years, across distances so vast they defy imagination, witnessing the slow evolution of galaxies, the formation of new stars, and the quiet drift of cosmic dust. And if we consider timescales even longer than we can truly grasp, the concept of a limit begins to blur. In a universe that may continue indefinitely, light could travel forever, even as the stars that created it burn out, and the galaxies that guided it drift beyond reach. It may eventually traverse regions devoid of matter entirely, traveling through an almost perfect vacuum where nothing slows it, bends it, or absorbs it. In this sense, the journey of light is both a measure of time and space, a link between past and present, a traveler that carries the history of creation and the promise of infinite exploration. Every time we observe a distant star or galaxy, we are witnessing photons that have survived this epic journey. We see their colors, their energy, their story, and we are reminded that while practical limits exist in our observations, light itself is fundamentally unbound. It is a traveler without end, a witness to the unfolding of the cosmos, a silent chronicle of time and space. The farther we look, the more we understand that light does not stop. It continues. Even when we cannot follow, even when it moves beyond our instruments, even when the universe expands faster than we can chase it. The question of a limit is therefore as much about perspective as it is about physics. From the point of view of the universe itself, there may be no end, no boundary, no horizon that halts light. From our perspective, constrained by technology, distance, and the expansion of space, there are practical limits, boundaries that define what we can detect. But the photon itself, once born, is free to travel until eternity, a small yet powerful symbol of motion, persistence, and the vast, interconnected cosmos that stretches beyond every imagination. The oldest light in the universe is a story that stretches across almost 14 billion years, a journey that began when the cosmos was only a fraction of its current age, a time when the universe was hot, dense, and full of energy. This light, known as the cosmic microwave background, was created when the universe cooled enough for atoms to form, allowing photons to travel freely for the first time. Before this moment, light could not move far without being absorbed and scattered by the dense plasma that filled all of space. The release of this light was like a great cosmic sigh, a first glimpse into the transparency of the universe, a whisper that the universe had grown old enough to let light escape its own chaos. As this light began its journey, it stretched across an expanding universe. Space itself was not still. It was growing, carrying the photons along like driftwood in an ever-widening river. The light has traveled farther than any human can imagine, passing through the birthplaces of galaxies, weaving around the gravity wells of stars and black holes, slipping through voids that are almost nothing, nearly empty stretches where nothing exists but more space. Its path is measured in billions of light years. Yet because the universe expands as it travels, the distance from the origin to us now is far greater than the simple multiplication of speed and time. Every second, every moment of expansion stretches the light further, its wavelength growing longer, moving from the visible spectrum into the microwave, cooling as it travels across the cosmic sea. This light has witnessed almost everything that has happened in the universe since it was born. It has passed through vast clouds of hydrogen and helium. It has skirted the edges of galaxies forming their first stars. It has felt the gravitational tug of dark matter and the subtle warping of space-time, and it has carried the faint echoes of quantum fluctuations that eventually became galaxies. Each photon is a tiny messenger from the earliest moments of creation, an imprint of the universe at a time when there were no planets, no humans, no life as we know it, only energy and the first seeds of structure forming in a hot, expanding void. To imagine how far this light has traveled is almost impossible. If you try to picture a number, billions of light years, you are still far short of the reality. It has crossed more space than all the distances in the solar system multiplied 1,000,000 times. It has traveled past stars that have lived and died, past galaxies that have merged or disappeared, past black holes that have swallowed matter and warped the very fabric of space around them. It has seen time itself stretch, and yet it continues, moving tirelessly, carrying its story forward. Even though this light is now incredibly faint, barely detectable, it still reaches our instruments. With radio, telescopes, and satellites, we can measure it, map it, and study it to learn about the universe when it was young. The photons carry information about temperature variations smaller than a degree across the sky, tiny fluctuations that became the galaxies and clusters we see today. Every measurement is a message from the past, a whisper from a time when the universe was just taking its first steps toward the complexity we now witness. Thinking about the journey of this light brings a sense of scale that is almost overwhelming. It has traveled farther than any spaceship could ever go, through distances and times that are hard to comprehend, across a universe that was very different when it began. Yet, After billions of years, it reaches us, a faint glow that tells a story of beginnings, of growth, and of the infinite journey of energy through the cosmos. Each photon is a survivor of the earliest chaos, a traveler that connects us to the dawn of everything. A reminder that even across unimaginable distances, there is continuity, that the universe has a memory carried by light. This ancient light also reminds us of the impermanence and persistence of the universe. Stars and galaxies will form and die. Civilizations will rise and fall. Yet the light from the earliest moments continues, indifferent to the passing of time, unchanged except by the gentle stretching of the cosmos. It is a record of existence before existence as we know it, a bridge to the first structure, the first matter, the first moments of possibility in a universe that has grown more complex with each passing second. To consider how far the oldest light has traveled is to confront the immensity of the cosmos, the patience of the universe, and the relentless motion of photons that have been moving for almost the entire history of everything. It is to imagine billions of years of cosmic history in a single beam of radiation, to feel the weight of time as space expands and stretches, and to recognize that in each photon, there is a connection between the birth of the universe and the present moment. A connection that spans incomprehensible distances, yet touches us here and now. The journey of the oldest light is far from over. It continues past us, onward into the void, carrying with it the imprint of creation, the story of the early universe, and the memory of all that has happened since its release. Every second, more of the universe reveals itself through this light, and as we study it, we learn not only about the distant past, but also about the future of space and time. It reminds us that light is timeless in its persistence, that the universe is vast beyond measure, and that even something as simple as a photon can tell the story of everything. When we think about colors of light, it is easy to imagine that red, blue, green, or violet light are just labels for what our eyes see. But in reality, they represent very specific wavelengths and energies. Each color of light corresponds to a different frequency, a different vibration of the electromagnetic field. And yet, in a vacuum, all colors travel at exactly the same speed. The famous speed of light, which is about 300,000 kilometers per second. This equality of speed is a strange and beautiful property of the universe. It means that once light leaves its source, whether it is a red sunset, a blue star, or a green aurora, all the different colors race across the cosmos together, side by side, without one overtaking another. The universe treats them equally in the emptiness of space, where there is nothing to slow them down, nothing to bend their path in subtle ways that favor one color over another. But the story becomes more intricate when light travels through a medium, something that is not a vacuum. When light passes through air, water, or glass, different colors can slow down by slightly different amounts. This phenomenon is called dispersion. It is why a prism can split white light into a rainbow of colors, because each wavelength bends and slows to a different degree as it passes through the material. In the vastness of space, most light travels through near-perfect vacuum, so this effect is minimal. But even the tiny amounts of interstellar gas, dust, and plasma can subtly influence the speed and path of each color. When we observe starlight that has traveled millions or billions of light years, scientists must account for these small changes, because even tiny differences accumulate over enormous distances, shifting the observed colors slightly, stretching or compressing the spectrum, and sometimes revealing hidden secrets about the space it passed through. The equality of speed in a vacuum also has deep implications for physics and the nature of reality. Because all colors of light travel at the same speed, our entire understanding of space and time, as expressed in Einstein's theory of relativity, depends on this constancy. It is what allows GPS satellites to function accurately, what allows us to measure distances across the universe, and what connects cause and effect across vast cosmic expanses. If red light traveled faster than blue, or if green were slower than yellow, the universe would behave in ways almost impossible to imagine. Cause and effect might become confused, the timing of cosmic events would be unpredictable, and even the basic structure of space-time would be different. Even within stars, the colors of light tell us stories about the processes at work. A blue photon emerging from the core carries more energy than a red photon born slightly further out, and yet once they leave the star, they move together, racing through space in perfect unison. The color encodes information, but the speed remains the same. Astronomers can read these colors like a cosmic barcode, learning about temperature, density, and composition. And all the while, these photons are traveling together, united in motion despite their differences in energy. Over immense distances, subtle effects like gravitational lensing can stretch or bend light, but still, each color obeys the same cosmic speed limit. When a black hole warps space around it, the light curves, its path bends, but the speed of each wavelength remains unchanged. The universe ensures that light, in its infinite variety of colors, travels together, carrying with it the stories of stars, galaxies, and cosmic events, maintaining an invisible unity across billions of years and trillions of kilometers. Even in human experience, this equality of speed is profound. Rainbows stretch across the sky because all colors emerge together after sunlight is refracted through raindrops. Sunsets glow in red and orange, while the blue light is scattered into the sky. Yet all these photons are racing through space at the same ultimate speed, arriving at your eyes in harmony. Our perception of color is tied to energy, to frequency, to wavelength, but it is never tied to speed in the vacuum of space. Every color is equal in its journey, a reminder that the universe has rules that are consistent, elegant, and surprisingly fair. In quantum physics, this concept becomes even more fascinating. Each photon, regardless of color, is a particle of light and a wave at the same time, yet it obeys the universal speed limit. When we measure it, we see its energy and frequency. We see its interference patterns, but we never see it travel faster or slower than light itself. The harmony of colors moving together is a cosmic symmetry, a principle that underpins the structure of the universe, from the tiniest atoms to the largest galaxies. Even as light interacts with magnetic fields, electric charges, or cosmic dust, the underlying speed remains unchanged in the vacuum. It is only when we introduce a medium that the separation of colors becomes noticeable, and even then, the differences are relatively small. The universe has designed light in such a way that its journey through emptiness is simple, direct, and reliable, despite the complexity of its origins and the diversity of its energies. All of this means that when we look at a star, a nebula, or a distant galaxy, we are witnessing billions of photons of all colors traveling together in perfect unity. Red, orange, yellow, green, blue, indigo, and violet, all moving at the same incredible speed, all carrying their own stories, yet all part of a single river of light flowing through the cosmos. It is a harmony that is almost impossible to fully comprehend. Yet it underlies everything we see, everything we measure, and everything we experience about the universe. This equality of speed across colors is a reminder that the universe operates on consistent principles, that chaos is guided by order, and that even the most energetic and diverse phenomena adhere to the same ultimate rules. From the tiniest photon inside a star to the oldest light traveling across billions of light years, every color moves together, reminding us that light, in all its variety, is a single, cohesive force, an unbroken thread connecting every corner of space and time. Light begins its journey at a source, whether it is the surface of a star, a glowing filament in a distant lamp, or the flash of a supernova exploding across space. At first, it is intimately connected to that origin, carrying with it information about the conditions, the energy, and the forces that created it. Every photon is a tiny messenger, a piece of the source that moves outward in straight paths until it interacts with something else. It carries color, brightness, and momentum. And in a way, it tells the story of where it came from. But once light begins traveling through the void of space, questions arise about ownership and belonging. Does it remain tied to the star that emitted it, or does it become something entirely its own, something that exists independently across the vastness of the cosmos? As light moves away from its origin, it spreads over distances so vast that it can travel for millions, billions, or even trillions of years. Along the way, it encounters no friction, no force that slows it, only the fabric of space-time itself that gently guides it along. The photon becomes increasingly isolated from its source, yet it still carries the signature of that star, of that moment, of that event. Astronomers can measure the spectrum of light from a galaxy billions of light years away and determine its chemical composition, temperature, and motion, revealing secrets about a time long before humans existed. In this way, the light retains a connection to its source, even if it is no longer physically near it. But consider the scale of the universe. Light travels through the void, past planets, stars, nebulae, and entire galaxies, sometimes bending under the influence of gravity, stretching as space itself expands, or even being absorbed and re-emitted by interstellar dust. At what point does the light stop being part of the original star and become part of the universe itself? Is a photon that has traveled across cosmic distances still owned by its sun? Or does it now belong to the interstellar space it crosses, to the galaxies it illuminates, or to the observers who eventually see it? In a sense, light becomes a bridge, a thread weaving together different regions of space and time, connecting origin and destination across unimaginable distances. As we think about light traveling forever, we also confront the idea of infinity. If a photon never stops, never dies, never fades completely, does it continue to carry the identity of its source indefinitely? Or does the act of traveling, of interacting with gravitational fields, bending around stars, and stretching with the expansion of the universe, change it so fundamentally that it becomes a part of the cosmos itself, no longer tethered to where it began? Perhaps light is both and neither. Perhaps it carries its origin in one sense while also becoming a witness to all that exists beyond that point. Its journey transforms it, yet it still whispers the memory of the source from which it was born. In another sense, light can be seen as freedom itself, the ultimate escape from origin. Once emitted, it cannot be recalled. It cannot be contained. It travels tirelessly across the universe, unbound, unaffected by the passage of time in the usual sense, never aging, never changing its speed. A photon may leave a star that has long since died, continuing its journey as if the star still exists, even though in its original location there is now nothing. In this way, light becomes independent, a traveler whose identity is defined not by its source but by the path it follows, the interactions it experiences, and the eyes, instruments, or minds that eventually perceive it. Light also interacts with observers. When a telescope on Earth detects the faint glow of a star from billions of years ago, that light suddenly acquires meaning in a new place. It tells us about the birth of stars, the formation of galaxies, and the expansion of space. In this sense, light belongs simultaneously to its source, the universe through which it has traveled, and the observer who perceives it. Its existence is shared, its identity is fluid, and its meaning evolves as it journeys. Even philosophically, light challenges our ideas of ownership and connection. It begins tied to a moment, a location, a source. Yet it is free to roam endlessly. It exists in the present, the past, and perhaps in ways we cannot yet fully grasp, connecting time and space in a way that seems almost conscious. A photon may carry the signature of a star, yet it also carries a story that belongs to the universe itself, a record of cosmic history stretching beyond the horizon of our comprehension. So when we ask if light still belongs to its source, we must consider that belonging may not be fixed. Perhaps light belongs to the universe in which it travels, to the observers who witness it, to the memories of stars long extinguished. Perhaps it belongs simultaneously to all of these, and in doing so, it becomes something greater than itself, a living thread in the vast tapestry of existence. It is both the echo of a moment and the journey itself, a piece of a star and a citizen of infinity, carrying information, color, and momentum forever, across a cosmos that is unending, ever-expanding, and full of possibilities we can barely imagine. Light is born, it journeys, it witnesses, it informs, it continues without end. In that way, it may belong to its source, it may belong to the universe, and yet it ultimately belongs to no one at all, because it is forever moving, forever changing, forever part of everything and nothing, a perfect expression of the infinite motion and energy of the cosmos. What happens to color when you reach light speed? It sounds like a simple question, almost playful, like asking what happens to a rainbow if you run fast enough. But the answer reveals something wild about how the universe behaves when speed becomes extreme. Light and color are connected. Color is just light seen with emotion and memory. We look at a sunset and see soft orange and warm red and gentle purple. But those colors are really just different wavelengths of light. The universe uses light the way a painter uses a brush, creating emotion and direction and depth in every moment we see. Now imagine you begin to move faster and faster. At first, nothing seems strange. The sky is still the same. The stars still shine with familiar colors. But as your speed approaches the speed of light, the universe begins to change. Space seems to stretch behind you. Time seems to thicken and push back, and light itself starts behaving differently. Everything in front of you begins to shift toward the color blue. Not a calm ocean blue, not a peaceful sky blue. A fierce and sharp blue that keeps sliding toward higher and higher energy. The wavelengths shorten, the light becomes more intense. It is called blue shift. Color squeezes itself into tighter pulses of energy as your motion steals pieces of the universe's color palette. Meanwhile, behind you, the opposite happens. The light stretches, it softens, it fades. Red becomes deeper red. Then, invisible heat. Then nothing but a whisper of energy dissolving into the dark. The world you leave behind loses its glow. It slides into a darkness that feels ancient and unreachable. Color becomes a memory that space refuses to return to you. This effect grows stronger as speed increases. It does not wait until you are at light speed to start changing everything you see. Even at 90%, the view begins to warp. Stars in front of you pile closer together. Their colors sharpen, their shapes thin into streaks. the universe seems to narrow into a tunnel of light. It is like flying through time itself as it collapses inward. The stars behind you stretch farther and farther apart until it feels like the universe you once knew is falling away into infinity. The faster you go, the more every direction except forward disappears. If you could somehow keep pushing faster, the colors in front would climb beyond visible light. Blue would become ultraviolet, then X-rays, then gamma rays. Light becomes radiation capable of tearing atoms apart. The universe in front of you does not just look dangerous. It becomes dangerous. Vision is replaced with high-energy light that no eye could ever understand without machines to translate the terror into something human again. And then, something even stranger happens. If you could reach the speed of light, which according to our best science is impossible for anything with mass, the color of the universe would collapse into a single point directly in front of you. Everything else would vanish. The world would not be full of rainbows or sparkling stars anymore. It would be a single blinding burst of energy from the direction of your motion, while every other direction falls silent. Forward becomes the only direction that exists. Space itself would feel like it is squeezing you into a line. Time would stop ticking for you. The universe would freeze into a moment that does not pass. Color disappears not because light stops being light, but because your motion bends the rules that let you experience color in the first place. Your eyes would not be able to make sense of the light. Your brain would struggle to attach meaning to something that is no longer built for humans. The universe is not designed for us to move that fast. Colors are a gift for slower lives. They are made for walking and breathing and smiling at the world instead of trying to outrun it. But this leads to a beautiful thought. The colors we see now are a reminder that we exist in a sweet spot between too slow and too fast. A place where the universe expresses itself through sunsets and flowers and glowing neon signs. A place where starlight has time to stretch across millions of years so that when it finally reaches us, it arrives gentle enough to admire. Our world of color exists because we are not racing toward the edge of time. We live in a universe that lets us see its beauty without forcing us to pay the cost of extreme speed. The fact that light only becomes color when time slows enough to let us notice it means that color is a love letter written by the universe to beings who are patient enough to look. So what happens to color when you reach light speed? It is swallowed by the universe's deepest laws. It stretches and collapses and transforms until it becomes something so powerful and so strange that the human experience of color can no longer survive. The rainbow that tells us who we are and where we stand would fall away. And maybe that is the reminder the universe is giving us. We do not need to race light to witness miracles. We are already living inside a miracle made of wavelengths and curiosity. Color is the universe talking to us, and it speaks most clearly when we are slow enough to listen. Light is one of the most remarkable phenomena in the universe because it connects everything in ways that are both visible and invisible, physical and conceptual, immediate and far-reaching, stretching across space and time in ways that shape the cosmos and the very way we experience it. Every beam of light you see carries information, energy, and history across unimaginable distances. When a star shines, it is not just illuminating its immediate surroundings. Its light travels outward through space, often for millions or even billions of years, reaching regions far beyond its own galaxy. That journey connects distant points in the universe, linking one star to a planet, one galaxy to another, one moment in the past to a present observer who may never meet the original source. Light is both messenger and bridge. Consider the sunlight that warms the earth, that nurtures plants, and powers the cycles of life. That light began its journey deep within the sun, created by nuclear fusion, moving slowly outward over thousands of years before finally escaping into space and crossing 150 million kilometers to reach us. When it touches your skin or falls on a leaf, it is the culmination of countless interactions and movements across space. Yet it also carries the story of the sun itself, its temperature, composition, and energy. Every photon contains a history that traces back to the heart of a star. In that way, light connects not just matter, but time, revealing the past and the present. Now imagine light from stars far beyond our galaxy. Each photon traveling across the void is a witness to events long gone, yet it arrives to tell the story of those ancient moments. When we observe a distant supernova, we are seeing an explosion that may have happened millions of years ago, yet it reaches our telescopes as if the event is unfolding right now. That connection through light allows us to explore the universe without ever leaving our planet, to understand the life cycles of stars, the formation of galaxies, and the expansion of space itself. Light is a bridge across time as much as space, linking the distant past with the present observer in a continuous conversation of energy and information. Beyond carrying information, light physically interacts with the universe in ways that influence the structure of matter and the dynamics of cosmic evolution. Photons exert pressure, pushing on dust and gas clouds, shaping star-forming regions, and even affecting the orbits of small particles. The radiation from stars sculpts nebulae into intricate shapes, while light pressure can trigger waves of new star formation, connecting generations of stars across time and space. Without light, the cosmic web of galaxies and interstellar matter might evolve very differently. Light is not merely an observer. It is an active participant in the ongoing creation and recreation of the universe. Light also mediates the forces that govern the universe. Electromagnetic interactions are carried by photons, meaning that light is intrinsically connected to the forces that hold atoms together, govern chemistry, and create the bonds necessary for planets, oceans, and life itself. In this way, every particle of light is linked to every other particle of matter in a subtle, pervasive network. The electrons in your body, the molecules in the air, the ions in distant stars are all participating in a cosmic dance choreographed by light, energy, and fundamental forces. That connection extends across scales, from the quantum realm to galactic superclusters, uniting the universe in an invisible lattice of interaction. There is also a profound philosophical aspect to the connectivity of light. When you see a star twinkle in the night sky, you are not only observing a distant sun, you are part of a dialogue that has persisted across the eons. The light that touches your eyes carries with it a sense of cosmic continuity. It reminds us that our existence is embedded in a larger, interconnected web of space and time, that we are participants in a universe in constant motion, change, and illumination. Light connects life to the cosmos, humans to distant stars, and present moments to histories that stretch far beyond our comprehension. Furthermore, light enables the exploration and understanding of the universe through telescopes, spectrometers, and satellites. Astronomers decode the colors, intensity, and polarization of light to reveal the composition, motion, and evolution of objects billions of light years away. Every photon is a messenger, a bearer of secrets that link us to distant corners of the cosmos. The very fabric of space and time becomes intelligible to us only because light travels through it and interacts with it. Without light, the universe would remain an opaque mystery, with no connection between observer and observed, past and present, near and far. Even at the speed of light itself, connection is profound. While photons move relentlessly through the vacuum, connecting stars to planets and galaxies to one another. They also define the ultimate limits of communication. Causality, the flow of information from cause to effect, is intimately bound to light. No signal can travel faster, making light the ultimate arbiter of connection. This constraint does not limit the reach of light, but emphasizes its centrality. It is the thread upon which the tapestry of the universe is woven, binding events and entities across the cosmic expanse. Light also interacts with dark matter and dark energy in subtle and profound ways. Gravitational lensing bends light around massive objects, revealing the presence of invisible matter, mapping the unseen structure of the cosmos, and connecting regions that cannot be linked through ordinary observation. Through these distortions, light exposes the hidden scaffolding of the universe, showing that even what we cannot see is bound together through the pathways that light illuminates. In this way, light connects not only what is visible, but also the hidden architecture of reality itself. And then there is the emotional and human side of light. When you witness a sunset, the faint glow of distant stars, or the auroras shimmering in the polar skies, you feel a connection not only to the Earth, but to the broader cosmos. Every photon that reaches you is a story of creation, travel, and endurance, a connection across space and time that bridges the gap between our small, fleeting lives and the vast expanse of existence. That connection is immediate, sensory, and universal. Light allows us to experience the universe directly, to be part of a continuum that stretches from the first stars to the farthest reaches of the observable cosmos. The interplay of light and shadow, the journey of photons from one end of the universe to the other, and the information encoded in every beam creates a network of connection that is both physical and conceptual. Light carries energy, matter, information, and emotion. It allows us to see, to understand, and to imagine. Every point in the universe that emits light is connected to every point that receives it, forming an invisible web of interaction that links all things. Ultimately, light is the universe's great connector. It bridges time and space, matter and energy, observer and observed, past and present, known and unknown. It is the invisible thread that binds galaxies, stars, planets, and life itself into a coherent cosmic story. From the tiniest particle to the largest galaxy, from the first flicker after the Big Bang to the last photons escaping distant quasars, light connects everything, everywhere, always, in a way that no other phenomenon can. It is the messenger, the sculptor, the force, and the witness of the universe, carrying with it the continuous story of all that exists and ever has existed, linking each moment, each object, and each consciousness across the vast cosmic web that stretches beyond imagination. Time near light speed becomes something entirely different from what we experience in daily life. As an object approaches the speed of light, the universe stretches and bends in ways that our brains struggle to fully grasp. Clocks on a spaceship moving near light speed tick slower compared to clocks left behind on Earth. Seconds stretch into minutes, minutes into hours, hours into days. And for travelers moving at extreme velocities, what feels like a single heartbeat could correspond to decades or even centuries passing elsewhere. In this sense, the idea of living forever in a single moment is not a fantasy. It is in effect written into the very fabric of space-time, a reality dictated by Einstein's theory of relativity. Imagine boarding a spacecraft designed to accelerate close to the speed of light. The engines hum continuously, propelling you past stars and galaxies, and as you gain velocity, something strange happens. The distant universe seems to warp around you. Light from stars ahead is blue-shifted, compressed into higher frequencies, while light from behind stretches into long, slow waves. Your perception of the universe changes. Time outside the ship races ahead, unseen and uncontrollable, while inside the cabin, everything remains calm. Days pass as seconds, years as hours, and your own biological clock remains almost unaffected. In this accelerated journey, the world outside evolves at a pace incomprehensible to your senses. Civilizations rise and fall. Stars live out entire lifetimes, and yet you remain in a cocoon of near-constant experience. The experience is profoundly disorienting and yet deeply liberating. To live forever in a moment does not mean halting existence. It means existing in a state where the passage of time around you has no grip over your own perception. You become a traveler, moving through both time and space in a unique way. One of the most mind-bending aspects is realizing that while you experience minutes or hours, generations may be born and lost elsewhere. The world continues without you in ways you cannot observe. Yet for you, life seems unbroken, eternal, and intimate. There is a quiet solitude in that, a feeling of being both part of and entirely separate from the flow of the universe. The phenomenon also raises philosophical questions about what it truly means to live. If your own consciousness experiences time slowly while the universe rushes forward, are you living longer, or are you simply perceiving a different rhythm of existence? Each heartbeat, each breath, each flicker of thought becomes magnified, intensified by the stretching of time. Moments expand to contain not only their own content, but the shadow of what passes beyond them. The idea of forever is not abstract here. It is tangible, measurable, and woven into every second of your perception. It is not only biological processes that stretch, but also memory and reflection. You could dwell on a single thought, a single sensation, or a single view of a distant galaxy for what feels like an eternity. Every detail becomes vivid, every interaction intensely present, and yet outside the ship, the universe marches forward at a pace you cannot match. Imagine observing a star explode in a supernova. To you, the expansion of the explosion might unfold over years, a slow unfolding of cosmic beauty. To those remaining on distant planets, it might happen in moments, a bright flash, and then darkness. You inhabit a unique temporal perspective, one that bridges the boundary between fleeting moments and eternal experience. Time dilation near light speed also creates a curious relationship with mortality. If you could travel indefinitely close to light speed, your personal aging would slow dramatically. Decades or centuries could pass outside your protective bubble, and yet your body would remain nearly unchanged. Theoretically, you could witness the evolution of entire civilizations, the rise and fall of empires, and the death of countless stars while you move forward with minimal aging. The illusion of living forever becomes an intimate consequence of physics, a window into eternity dictated not by imagination but by the structure of space-time itself. The implications extend beyond the individual. Consider relationships and society. Those who remain near light speed experience life at one rhythm, while the rest of the universe pulses at another. Communication becomes almost impossible because each message travels through time at different rates for sender and receiver. You could send a greeting and find that centuries pass before it arrives, or you could receive messages from distant pasts. In this sense, living forever in a moment isolates as much as it preserves. It creates a paradox where continuity is eternal, yet connection to the wider world becomes fragmented, a bridge stretching across time that few can follow. It is also fascinating to consider the emotional and cognitive impact. Perceiving time stretched endlessly could amplify emotions, thoughts, and experiences. Joys could feel richer, sorrows deeper, and each moment gains layers of nuance that would normally pass unnoticed. A sunset could be observed for months, a conversation linger for years, a thought repeated and expanded upon endlessly. The subjective experience of reality becomes vastly more complex, richer in texture, depth, and awareness, a life lived in exquisite, almost unbearable detail. Yet the concept is not entirely free from limits. Even if your own time is stretched, the universe around you continues to evolve, and eventually new physical boundaries, gravitational fields, and cosmic events could alter your path or your experience. Absolute eternity may not be possible in a literal sense, but the near infinite stretching of experience offers a glimpse of something close to it. It is a reminder that life, perception, and consciousness are flexible when considered in the context of the vast, relativistic universe we inhabit. Ultimately, living forever, in a moment near light speed, is an intersection of imagination, physics, and the human desire to extend experience. It is a state where the ordinary rules of life, aging, and time dissolve, replaced by a unique rhythm that defies everyday understanding. It offers both solitude and intimacy, isolation and connection, all wrapped in the endless motion of space-time. It is peaceful in its suspension, chaotic in the awareness it brings, and profoundly beautiful in the opportunity to experience life stretched beyond the usual confines of seconds, minutes, and years. Every moment becomes a universe in itself, each heartbeat an eternity, and every observation a window into timelessness. The traveler who moves near the speed of light carries within them a sense of living both fully and eternally, a paradox written into the laws of physics, a gift from the cosmos that few could ever truly imagine experiencing. It is a meditation on time, existence, and the beauty of perception, a reminder that while the universe may continue endlessly, consciousness has the power to expand within it, touching a form of eternity that feels as close as a single, infinite moment. When light hits nothing at all, it does not stop. It does not slow down. It does not fade or disappear. It continues to travel endlessly through the emptiness, moving forward without anyone to see it or anything to touch. A photon, which is what we call a particle of light, can move across space for billions of years and still keep all the energy it had when it was created. It carries the memory of the star or the event that released it. It holds information about the temperature, the pressure, the elements, and even the motion of the place where it began. That information travels with the light forever, unless something finally interacts with it. The emptiness of space is not hostile to light. It does not slow it down. There is no friction, no air, no particles to bump into. Light glides through these vast voids effortlessly. Even in places where there is not a single atom for millions of light years, it continues. A beam of light can leave a galaxy, travel across the intergalactic void, and keep moving as if nothing has changed. The distance does not matter. Time does not matter for the photon. From the point of view of the light itself, the journey is instantaneous. It does not age, it does not tire, and it does not experience the passage of moments. Even when no one is there to see it, light is still real. It still exists. It still carries energy and can still influence the universe. A photon traveling through empty space is like a letter sent into the void. It may never be received, but it still holds the message. The universe is full of photons that have been moving since the very beginning. Some were released by stars that no longer exist. Some were created during cosmic events billions of years ago. They travel through nothing, and yet they carry the echoes of their birth across time and space. Light can travel across distances so vast that human minds struggle to imagine them. It can cross hundreds of millions of light years, billions of light years, and continue without changing speed or losing energy in empty space. Along the way, it may pass near galaxies, black holes, or clouds of dust, bending slightly under gravity or being absorbed and re-emitted. But in the regions where there is absolutely nothing, it simply moves forward, a perfect example of motion in a vacuum. Even when nothing interacts with it, light still has properties. It still vibrates as waves. It still moves in straight lines. It still can be measured if we eventually detect it. The absence of obstacles does not mean the absence of existence. That is what makes light so remarkable. It can exist and move even in total emptiness. It shows us that the universe does not require observation to persist. When a photon passes through nothing at all, it also reminds us how vast space really is. The emptiness between stars and galaxies is immense. Light can travel millions of years before it touches anything again. During that journey, it may seem as if nothing exists. The dark may appear complete and absolute, but the photon continues. It persists. It proves that even in the most silent and empty places, there is still energy. There is still motion. There is still something happening, even if no one is watching. This endless journey through nothing also challenges our understanding of time and distance. From our perspective, a photon may take billions of years to reach a telescope. From the photon's perspective, the journey takes no time at all. Every second that passes for us is irrelevant to its existence. It moves at the ultimate speed. It travels across a void so empty that it feels infinite. Yet it continues. Every moment of movement matters. Every path it takes is real, even if it never interacts with a single atom along the way. Light traveling through nothing also carries the potential to interact with the universe at any moment. A photon may drift through the void for billions of years before finally striking a dust grain, a planet, a telescope, or a particle of gas. When it does, it gives up its energy. It can create heat. It can be absorbed, reflected, or scattered. It can be seen by an eye or a camera. It can influence atoms and molecules. But until that moment, it exists fully and completely, moving through the emptiness as if it belongs there, perfectly at home in the void. In this way, light is a traveler, a messenger, a record keeper, and a reminder. It shows us that even in absolute emptiness, something can continue, something can carry information, something can endure. Light does not need a medium to exist. It does not need observers. It does not need interaction to be real. It moves, and its journey alone is proof that existence can persist in even the most silent, empty, and dark places of the cosmos. Even if the light never meets anything again, it is still part of the universe. It is still shaping the cosmos in invisible ways. It still demonstrates the rules of physics, the constancy of energy, and the infinite possibilities of motion. Every photon moving through nothing is a quiet witness to the enormity of space, to the history of stars and galaxies, and to the beauty of the universe unfolding in places no one will ever see. When we think about light leaving a star, it might seem simple at first. You might imagine that photons, the tiny packets of light, are born in the core of a star where nuclear fusion powers the intense heat. And then they shoot straight out into space at the speed of light. That picture is true in part, but in reality, the journey of a photon from the heart of a star to the space around it is extraordinarily long, far longer than anyone usually imagines. Inside a star, the environment is dense and chaotic. In the core, where temperatures can reach tens of millions of degrees, photons are constantly interacting with matter. They are absorbed and re-emitted countless times by electrons and atomic nuclei. Every time a photon is absorbed, it loses direction and sometimes energy, and when it is re-emitted, it is sent off in a random direction. A photon cannot just travel straight outward. It is bouncing in a dizzying random walk, being scattered in all directions, wandering through the dense stellar plasma like a traveler lost in a forest of endless mirrors. For a star like our Sun, this journey can take an average of 100,000 years, sometimes longer, for a photon to finally escape the dense interior and reach the surface. Once it reaches the surface, the journey becomes more straightforward. The photon leaves the star and begins its unimpeded travel across the void of space at 300,000 kilometers per second, moving from the star to the planets, moons, and eventually into the wider galaxy. The contrast between the slow, chaotic journey inside the star and the instantaneous, nearly frictionless travel across space is astonishing. One moment the photon is trapped, bouncing endlessly through dense matter, and the next it is racing freely across the vacuum of the cosmos, covering distances that would have been impossible inside the star in just seconds. This slow inside, fast outside journey of light is true for all stars. The bigger and denser the star, the longer it can take for a photon to escape. Massive stars, those many times the size of the Sun, have even denser cores, and the photons born there can spend millions of years wandering inside the star before finally breaking free. And even when the photon reaches the surface, the universe it enters is vast and almost empty, with galaxies, clouds of gas, and dust filling the void. Light continues to travel across unimaginable distances, carrying with it the story of the star's interior, the energy forged in nuclear fusion, the history of that star's creation, and the elemental processes that will one day form planets, oceans, and possibly life. Inside the star, the constant scattering creates a kind of cosmic patience. The photons seem to age before they even reach the surface. They are trapped in a slow dance with matter, each collision a momentary pause, an interaction that changes the photon's path and sometimes its energy. This random walk ensures that the energy of the star is distributed evenly, that heat and light are radiated in a balanced way, allowing the star to shine steadily for millions or even billions of years. Without this chaotic internal journey, stars might shine too unevenly, their energy lost in bursts rather than a constant glow. Once the photon escapes, it begins a story of freedom, yet it carries the memory of every interaction, every scattering, every tiny delay from its time inside the star. That memory is embedded in the light itself, in its wavelength, its energy, and even in the subtle ways it interacts with matter and magnetic fields as it travels outward. Light is not just a means of seeing the star, it is the story of the star, the record of the processes that forged it, a messenger that tells the universe about the life and conditions inside one of the most extreme environments imaginable. Even though the photon may take 100,000 years or more to leave the star, once it emerges, it travels across the cosmos in a blink relative to that internal timescale. That same photon from the Sun that took thousands of generations to escape now reaches Earth in just 8 minutes. Light from stars much farther away can take hundreds or billions of years to arrive, but compared to its internal journey, even these distances are minor in the grand scale of cosmic time. The photon's story is one of patience and sudden freedom, of a long struggle through matter followed by instant travel across the universe, carrying information and energy over unimaginable distances. This long internal journey is a reminder of the complexity of even the simplest seeming phenomena in the universe. Light is everywhere around us, instantaneous in our daily experience. But its creation and escape from a star is an epic, slow, and fascinating process. Every beam of starlight that reaches us is a witness to hundreds of thousands of years of travel through the chaotic interior of a star, and it reminds us that even the fastest thing in the universe must first earn its freedom before it can race across space. Darkness is often described simply as the absence of light, the empty space where photons do not reach, where the glow of stars or lamps cannot touch. Yet when we think about it more deeply, darkness is more than just an empty stage for light. It is a presence of its own, a canvas upon which the universe paints everything else, a quiet, waiting space that allows light to exist at all. Without darkness, there could be no contrast, no shadow, no form. Darkness gives light its meaning, its brilliance, and its depth. It is the frame around the painting, the silence between musical notes, the space that allows the cosmos to breathe. In the vastness of space, darkness is not merely a backdrop. It stretches endlessly between galaxies, in the void between stars, across interstellar and intergalactic expanses. In these regions, there is almost nothing to see, nothing to touch, nothing to detect. Yet the emptiness itself is not nothing. It holds potential. It holds energy in ways we are only beginning to understand. Even in complete darkness, the laws of physics operate. Gravity bends the invisible fabric of space-time. Magnetic fields ripple silently. Tiny quantum fluctuations dance invisibly, shaping the cosmos without light to show the way. Darkness is the quiet stage where the universe performs its most subtle acts. Darkness is also a measure of perception. When we close our eyes, darkness surrounds us. Yet we still sense warmth. We still hear sound. We still feel movement. Darkness is the reminder that vision is only one way to experience reality. It teaches that absence of light is not absence of existence. When we look at a black hole, for example, we see only darkness, a region from which no light escapes. Yet we know it is teeming with immense gravity, spinning singularities, and potential energy. Darkness is a signal, a presence that hints at what is hidden, what is powerful, what is beyond the reach of ordinary perception. Even in daily life, darkness is more than simply an absence. A quiet room at night is dark, yet it is filled with possibilities. Thoughts move freely, imagination stretches, dreams begin. Darkness allows the mind to create its own light, to invent stories and visions. It is the essential counterbalance to illumination, giving space for reflection, for introspection, for the growth of ideas. It is not emptiness, but the womb of possibility, a silent companion that patiently waits while we explore, learn, and create. In physics, darkness is also intertwined with mysteries we have not yet unraveled. When we study dark matter or dark energy, we are confronted with the idea that darkness may be more than the absence of visible light. It may be a substance, a force, a property of the universe that shapes galaxies and accelerates the expansion of space. This darkness interacts with the cosmos invisibly, quietly holding sway over structures we can see. In this sense, darkness is not a void. It is active, powerful, and essential to the existence of everything we observe. Even philosophically, darkness carries meaning beyond the physical. It represents the unknown, the unseen, the things that elude understanding. It is the silent mystery of the universe, the parts of existence we cannot yet measure or perceive. Darkness is where curiosity thrives, where wonder begins, where imagination grows. It is the shadow that defines the light, the question that drives the search for answers, the quiet space where humans confront the enormity of the cosmos and the limits of perception. Darkness also teaches patience. In the absence of light, we learn to listen differently. to sense differently, to exist without immediate visual guidance. Space is dominated by darkness, yet it is alive with phenomena that reveal themselves slowly, subtly, through radiation, gravitational waves, or faint particles. Darkness allows for observation, for discovery, for understanding to deepen over time. It is not emptiness. It is an environment that challenges us, that sharpens perception, that amplifies the beauty and meaning of light when it arrives. Even emotionally, darkness is complex. It can be calming, it can be intimidating, it can be comforting or overwhelming. It gives context to experiences, allowing relief, rest, and reflection. Darkness provides contrast in our lives just as it does in the universe, shaping perception, giving depth, and enhancing the beauty of illumination when it appears. Without darkness, light would be meaningless. Without empty space, matter would have no structure. Without absence, presence could not exist. Darkness, then, is something more than just nothing. It is a dimension, a state of being, a quiet, ever-present force that shapes reality and consciousness alike. So, when we think of darkness, we are not thinking of a simple emptiness. We are considering the vast, patient, silent canvas that allows the universe to express itself. We are acknowledging the unseen, the subtle, the quiet forces that shape everything. We are recognizing that absence is not nullity, that invisibility does not imply non-existence, and that even in the stillest, quietest parts of the cosmos, there is meaning, there is structure, and there is infinite possibility. Darkness is both the silence and the stage. It is both the absence and the presence. It is both the question and the answer, quietly waiting for attention across the universe and within ourselves.